Hey guys, welcome. So today we're going to talk about complex numbers. The reason why you have this complex number section sort of at the end of this chapter on radicals is that there's a lot of nice sort of carryover and properties that you can use for radical expressions that you can then sort of carry over to the complex numbers, right? So first of all, we're going to talk about what the imaginary unit is, and that's the number that we sort of indicate with I here. And that's sort of one thing that we've sort of been discouraged of thinking of, but that's the square root of a negative number, right? So for example, say you have something like x squared is equal to 4. Sorry, negative 4, right? Now, of course, that's not something that we can sort of do with real numbers, because if you multiply a number by itself, you're either doing positive times positive, which is a positive number, or you're doing negative times negative, which is also a positive number. So something like this is not able to be solved, so you can't solve with real numbers. And that's where imaginary numbers comes into play, right? So you can now, if you sort of define this thing as being legitimate, you sort of have this square root of negative 1 as sort of being fair game, you can now talk about any square root of a negative number for any number by just using sort of the property that we have where you can break up any number into a product of two numbers and then take those individual roots. So basically what you're going to do is you're going to pull out the negative number by taking this square root of negative 1 out, and then we know that we can write that as I. Right, so there's a couple of examples here, but I'm going to sort of do them as they come up in the lesson here. Right. Now, one more thing that we need to talk about in terms of complex numbers here is sort of how we can write any complex number. So any complex number can be written as its real part plus its imaginary part, right? So it might have, for example, real part 3, imaginary part 2, or something like that. But we can write every complex number in this form as its real component plus its imaginary component. So that's sort of what we're going to start with doing first. All right. So let's look at 2 minus 2 minus square root of negative 49. Right. So the first thing that we notice is that we have this square root of a negative number here, right? So what we want to do is use our property that we have that we just talked about, where we can think of this as square root of 1 times square root of 49. And now we actually know what both of these are, right? Square root of negative 1 is what we've been calling I, and square root of 49, of course, is just 7, right? So we can now write this as 2, we didn't do anything with that, minus 7i, right? And now we have this written in the form of a plus b times I. And here, if you want to really be fancy, you could say that a is 2 and b is negative 7. All right, now you don't have to write that out, of course, every time, but that's how we could write out this number in the form a plus bi. All right, let's look at another example. So now, same idea here. The 7 I can't do anything with, but we can think of this as a square root of negative 1 times the square root of positive 24. And again, the square root of negative 1 is just I. Now, there's no perfect square. The 24 is not a perfect square, but we can think of it as the product of a perfect square and something else. We can think of it as square root of 4 times square root of 6. So then that will give us a 2 times square root of 6. Right? So now we can write this number. Again, the 7 we didn't do anything with. But now we can write this as plus, and now I just have to combine all of this stuff here. And probably the most common way to write this is 2i square root of 6, right? Now you can write it as 7 plus 2 square root of 6i. But if you do write it that way, I would just make sure that you're careful just to indicate that the I is not within the square root, right? So either one of these ways is fine. I actually myself probably write it this way. but either one of these forms is fine. As long as it's clear that the I is not in the square root, that's really the important thing here. All right, and let's look at part C. So again, here you don't have a real component, at least because we just have the square root of the negative right away. So we can say that this is just, now I'm going to just say that this is I times square root of 50. Right, so I'm just sort of skipping the intermediate step there, that if you pull out square root of -1, we can say that that's I. All right, so now we simplify square root of 50 like we would before. So of course, two numbers where one of them is a perfect square, I can think of that as 25 and 2. So then that gives me 5 square root of 2. Right, so now we can take this information and write this all as a 5 square root of 2 times I, or of course, if you want to write it as 5I square root of 2, that also works, right? But either one of those answers would be fine. Okay, so that's sort of the first thing that we need here as far as our complex numbers. We want to be able to write it in a form of A plus BI. Okay, now one thing that we're going to come across here, and I think this is really more for when we do multiplication and division, but nevertheless, we can mention it now. All right, so we know that I is the square root of -1, right? So we can then square both sides, and we can say that I squared is square root of -1 all squared. And so we're sort of, again, we're assuming that the square root and the square undo each other, and we get that -1. Right, so we're sort of allowing for this natural thing to happen here. I should say it's sort of unnatural so far, but the natural thing, if we sort of allow the sort of properties to sort of carry over, this is how we could define I squared. But anyway, so the next thing we're going to talk about is adding and subtracting complex numbers. So essentially what you do is you're going to, this is sort of explaining it in a little bit longer way than it really needs to. Basically what you're going to do is you're going to write all your numbers in the form of A plus BI if they're not already there. And then really this is all just a fancy way of saying combine like terms, all right? So you can see that in the first example here, right, they're already in A plus BI form, so we can just go right to combining our real parts, which are 8, -6, and 15. And if we add all them together, that will give us a 17. So that's our real part. And then if we look at our imaginary part, we have a 5i and a -i. So if we combine them, that's a plus 4i, right? So we get 17 plus 4i. And that's it, right? So adding in is pretty easy, especially if it's already in this form. Right. So now, of course, what if it's not in that form to start with? Well, it's sort of the same thing, except we want to convert first to A plus BI form. Right. So this we can think of as an I square root of 50. Right. And we actually did that earlier. We said that that comes out to be a 5 square root of 2 times I. Right. So this whole first part will give us a 7 minus 5 square root of 2 times I. And then we want to do the same thing for this part, right? We can think of this as an I times square root of 72. And of course, 72, you can think of as square root of 36 times square root of 2. So that's a 6 square root of 2. So now this number we can write as a -8 plus 6 square root of 2i. And now we're subtracting these. So maybe let me just grab this. And we can move it down. Okay. So now we can distribute our negative. No, I don't want to do it. Okay, so we can do 7 minus 5 square root of 2i. If we distribute this subtraction, we'll get now plus 8 and now minus 6 square root of 2i. And then just as before, Our two real parts are 7 and 8, so together they are 15. And we look at our imaginary components. We have minus 5 square root of 2 times I and minus 6 square root of 2 times I. So together that's minus 11 square root of 2 times I. Right, so remember, when you add or subtract radical terms, you're essentially treating them as combining like terms as well. All right, so that one will give you 15 minus 11 square root of 2I. All right, so that's what we want to do when we're adding and subtracting. All right, now when you multiply complex numbers, what you're essentially going to do again, once you've converted everything to A plus BI form, you're going to essentially multiply just how you would if you had a regular polynomial, right? And then at that point, using what we talked about before for I squared, you'd want to substitute any I squared you have with a -1, and then it's a matter of combining like terms at that point, right? So let's look at an example in action here. Okay, so if we multiply here we need to distribute, of course. So I have a 2I times 9, which is an 18I. And then a 2I times minus 3I is a minus 6, and then I times I is I squared. So of course now we need to write any I squareds we have as a -1. So -6 times -1, this will now be an 18I plus 6. And if we really want to be thorough here, this would probably be fine. Whoops, this would probably be fine as a final answer, but we would just to, I guess, be consistent here, we'll say this is a 6 plus 18I, just to put the real part first, imaginary part second. All right, so that's not bad. All right, especially if it's already given to you in A plus BI form. Now for part B, we're not so lucky, we have to convert first. So this -16 square root of -16 I can write as an I square root of 16. And of course, square root of 16 is 4, so this is a 4I. And then for square root of -2, I can write that as an I square root of 2. And we actually can't do anything else with that, all right? So now we can rewrite this as a 4I times a square root of 2 times I, and then plus 5. And that's essentially the same as the last problem. We just have to distribute again. All right, I'm going to come up here. So if we distribute, we get a 4 times the square root of 2 times an I squared. And then a 4I times 5 is a 20I. Okay, so now we again have I squared, so we'll write that as a -1. So this is 4 square root of 2 times -1 plus 20I. So once we multiply it by the -1, we get a -4 square root of 2 plus 20I. And there's a final answer. All right, we'll do one more for multiplying, and then we'll talk about dividing. All right, so again, same as the last one, we want to convert to A plus BI form. So this we can write as an I square root of 18. And then, of course, 18 we can think of as 9 and 2. So this will become a 3 square root of 2 times I. Right, and we just saw square root of -2. The best we could do with that is square root of 2I. So now what we have is a 2 minus 3 square root of 2I times the square root of 2I plus 5. So now here when we FOIL, so we'll get a 2 times the square root of 2I plus 10 minus a 3, and square root of 2 times square root of 2 will just give us a 2, and then I squared. And then we get a minus 15 square root of 2I. So now we can simplify this a little bit. We can say that this is a -1. So we'll get a -3 times 2 times -1. So that will all come out to be a plus 6. Right? And then we have this 10 here. the 2 square root of 2i, and then minus 15 square root of 2i. So now when we combine, we can combine our 10 and our 6, and that will give us a 16. And then when we combine our minus 15 square root of 2i and our 2 square root of 2i, that is a minus 13 square root of 2i. Right, so again, hopefully not too bad, especially once you convert to a plus bi form. It's sort of, pretty straightforward. Okay, so now let's talk about, last but not least, we'll talk about dividing. All right, and this is going to be very similar to when you divided with radicals. So what you want to do is, again, after you convert everything to a plus bi form, we want to multiply by the conjugate, right? So now, just like your conjugate with a radical expression, so if you had something like a plus b square root of c, right? So that's the original. Then the conjugate is the same thing, except we change the sign of the radical term, right? Now, in complex numbers, sort of the same idea. You have something like a plus bi, but your I really is a square root. So when you take the conjugate, it's going to be a minus bi. All right, so we're going to use sort of the similar idea here. Now, for this first example, this is example 5, right? I would technically multiply top and bottom by negative I. Right? So if I do that, the bottom would just give me a negative I squared, which we'll fix in a second. And then the top, I need to distribute. I'm going to get a minus 5i, and then I'm going to get plus, negative times negative is plus, I squared. So now if we replace all of our I squareds with negative ones, get a negative one down here, make sure you're careful there. So we get a negative 5i minus 1 over 1. Anything divided by 1 is itself, so we can just write this as negative 1 minus 5i. All right, so simple enough. Now on this one, we don't have to multiply top and bottom by just I. Now here we need to be a little bit more careful. Here we need 3 plus I. That would be the conjugate of 3 minus I. So I need to multiply top and bottom by 3 plus I. And now we're just foiling, right? So in the bottom, I get a 3 times 3, which is 9, plus 3i minus 3i, and then a minus I squared. Right? So now on the top, we get 15 plus 5i plus 6i plus 2i squared. So now if I sort of change all of my I squareds to negative ones, I'm going to get a 15, and let's combine some of these. So we'll get a plus 11i, and then minus 2 over a 9. The 3i and the minus 3i cancel. We get minus a negative 1 or plus 1. So then we get a 13 plus 11i over 10. Now, if you wrote it like this, for me, I would be okay with that. Some other teachers, and this textbook actually prefers to write it in this form so that it's explicitly a plus bi. But either one of these answers are really saying the same thing, right? So either one of those would be good in my book. All right, let's do one last sort of cool thing that comes up here with powers of I, right? And then that will wrap up our discussion of complex numbers, right? So far we know that I is square root of negative 1, and we know that I squared is negative 1, right? So if we think about I to the third, we can write that as I times I squared, which is I times negative 1, which we could just say is negative I. All right, so that's sort of interesting. And for I to the fourth, we could write that as I squared times I squared. So that's -1 times -1, which is +1. Right? Now, if we look at I to the fifth, that's I to the fourth times I, which is just 1 times I, which is I. Right? So hopefully you can start to see the pattern here. Then, of course, what's I to the sixth? Well, that's I to the fourth times I squared. So that's 1 times -1. So that's -1. Right? So you can sort of similarly show that I to the seventh is equal to I to the fourth times I to the third. So that's 1 times -I. So -I. And then I to the eighth is I to the fourth times I to the fourth, which is 1 times 1, which is 1. And of course, this will, of course, repeat, right? So if you have any power of I that is a multiple of 4, that will always be 1, right? Because you could always say that it's I to the fourth to the n power for whatever number you want n, and that would just be 1 to the nth, which of course is always 1, right? Now, you could say that I to the even power of 4 plus 1 is always going to be just I, right? For a similar reason, you could say that it's I to the 4n times I, and we just showed that I to the 4n was 1, so this will just give you I, always, for no matter what your n is. And then similar, you can show that I to the 4n plus 2 is equal to, so a -1, right? Because then you'll have I to the 4n times I squared, so you'll get that that's -1. Right? And last but not least, we could say that I to the 4n plus 3 is equal to -I, because we could write that as I to the 4n times I to the third, which would give you a -I. All right, so that's another sort of final interesting comment about complex numbers. So that wraps up this video regarding our discussion on complex numbers. I hope you enjoyed, and I will see you in the next time.